Hello everyone, and welcome back to Deviations. In this video, we are going to be talking about the differential calculus applications to physics. We're going to be doing a lot of word problems, just like we did in the last two videos, where we talked about the applications to biology and chemistry. While similar to those videos, physics has a much bigger application field to differential calculus, and even the other parts of calculus that we'll learn later on. But the entire motivation behind Isaac Newton creating differential calculus was to be able to apply it to physics. So calculus has a huge role in both classical mechanics and electricity and magnetism, which we will definitely cover a lot more later on. As always, I recommend freshening up on any derivative rules or methods that you may have become rusty on for the next video, but let's get started. So the bulk of our work today is going to be involved with kinematics. So kinematics is the study of motion, an object-particle motion. So we are going to consider a position function, and as always, it's going to be a function of time. So x of t is our position function. We talked about this earlier in some of our other word problems, but if I want to take the instantaneous rate of change of the position, I will get velocity. So the velocity is the instantaneous rate of position with respect to time, meaning that v of t is equal to the derivative of x. Furthermore, acceleration is the instantaneous rate of velocity with respect to time, and that means that a of t, our acceleration function, is the first derivative of velocity and the second derivative of position. With that, let's do some examples. Okay, so we're going to start with a particle motion, and we're going to be given a position function. X of t is equal to t cubed minus 6t squared plus 9t. And they're asking us to find the velocity after 2 seconds and after 4 seconds. So to do this, what we are going to do is we're going to take the first derivative of position, and that will give us v of t equals dx dt, which is equal to 3t squared minus 12t plus 9. And in order to evaluate that at 2, we're going to take the derivative and evaluate that at t equals 2 seconds, and that will give negative 3 meters per second. Furthermore, if we evaluate that at t equals 4, we will be given 9 meters per second. After this, they're asking us to graph position, velocity, and acceleration against time. So this is just going to be the graphs of our original function, the first derivative, and the second derivative, and it's going to look something like this. And as you can see, we're just taking more derivatives to be given our different aspects of what we're looking for, that being position, acceleration, and velocity. Okay, let's do another example. This example is going to involve density. So density is denoted by rho, Greek letter, and our expression says rho equals m over L. Okay. And the average density is going to be delta m over delta t, and then we have that secant approximation, f of x sub 2 minus f of x of 1 over x of 2 minus x of 1. And of course that means that we can change those deltas to differentials, giving us dm dx. Okay. And you can imagine this as a rod, and we're trying to find the density at a point on the rod. Okay, so now what we're going to do is we are going to consider a function. We're going to consider m equal to f of x equal to the square root of x. Find the density at 1. What we are going to do, we'll take the derivative of the square root of x, and then we are going to evaluate that derivative at 1, and that will give us the density. That will say that rho is equal to dm dx, which is equal to 1 over 2 root x. And if we evaluate that at x equals 1, that will give 0.50 kilograms per m. Alright, and that is our video on the applications of differential calculus to physics. Now, next time we will be shifting gears completely, and we're going to be moving into Unit 3. And Unit 3 is really going to cover the applications of differentiation, not like the word problems that we've been just using our rules with, but how they're actually going to help us with graphing and optimizing and taking limits, because derivatives are so much more than just a method to find the slope of a line. They're going to help us with a lot more things that are going to make it very important to us later on. So we will see you back for Unit 3, where we will be talking about the maximum and minimum values of a graph. And we'll be using differential calculus to study that. Thank you for watching. Please like and subscribe. See you next time.